So welcome to our session. We're kicking off things today. We have two amazing days of sponsored sessions with NVIDIA. We're going to be previewing those today, as well as going over the overall strategy for how we engage with game developers and what we're trying to achieve overall with gaming. My name is John Spitzer. I lead a team called Developer and Performance Technology at NVIDIA. I've been here since 1999 and working with developers in one way or another through that 25 years. So Developer and Performance Technology is a group that consists of roughly 700 very talented and experienced engineers, analysts, and artists. And we're split between 6 different teams. One is the Performance Lab, where we measure the full gamut of NVIDIA's products, ranging from the smallest embedded Jetson systems all the way up to LLM training runs involving thousands of GPUs on the cloud, and of course, everything in between, including GeForce and everything else. The second team that we have is technical marketing. This is a team of analysts who look at our products immediately before as well as after their launches, trying to understand how best to review these products so that they'll be viewed in the best possible way by reviewers and influencers, working directly with those people, and then following up to make sure that all their questions are asked, or are answered, excuse me. I'm also getting over a combination of strep throat and the flu. So hopefully not contagious. No, I'm definitely not contagious. It's been 2 weeks, but my voice is a little bit faltering, so apologies for that. So we have also the digital human technology team, who our leader here is Simon. Simon's team is focusing on all the technologies in order to make sure that humans look, sound, and act as like real humans in a game. So this includes their physical attributes, their skin rendering, how they are animated, how they gesture, how they speak, making sure all the lip sync works flawlessly with the audio track and so on. We also have a ray tracing team. This is essentially all the software that is involved in making our ray tracing work across all 3 APIs, DirectX, ray tracing, VK-Ray, as well as our own optics APIs across the full range of both games as well as professional applications. We also have an in-game game studio, in-house game studio, which we call Lightspeed Studios. I kind of think of them as dog food studios because we're eating our own dog food here. We're taking often inchoate pieces of technology across the company, bringing it into the studio, pairing it with content. This is a studio of roughly 70 artists and 30 engineers. We pair the content with the technology and we fully vet it to make sure it's actually going to work as it was originally intended, and that it does exactly what it was intended for the game developers before it actually ever enters the hands of the first game developer. So we are the point of the spear within Lightspeed Studios of testing this technology and making sure that it works as it was intended. That studio is also responsible for our RTX Remix remodding platform, and we'll be talking about that in detail later. And then last but not least, we have our gaming developer technology team. This is a team of about 70 engineers who are distributed all over the world, working one-on-one with game developers to teach them how to make the most out of our GPUs, out of our AI, and our rendering technology packages. And so we are the technology partner for all these game developers worldwide. So I tell people all the time that I have the best job in the world, and I'm not lying. I'm working with an incredibly talented team, and we are working on, I would say, the most exciting technology in the world, and I'm super excited to share that with you today. So without further ado, let's do it. NVIDIA strives to be the technology partner for the gaming industry, whether you be a publisher or a developer. We, of course, have a full suite of data center products, DGX and switches and NICs and all of this stuff that you would need for doing your training and inference for whatever sort of AI model you would want. We also, of course, offer the world's fastest gaming GPUs, the GeForce line, most recently the Blackwell launch that we had back at CES. Yesterday, we announced our latest generation of professional products, which is the RTX Pro Blackwell line. spanning whatever system you want to run it in, whether it be a notebook computer or desktop or in the cloud on a server. And these feature up to 96 gigabytes of memory. We also have our GeForce Now gaming platform, which allows you essentially instantly available gaming at 4080 performance on any device that you want, whether it be a MacBook or even a TV. My wife and I actually like to play on our TV. It's got a built-in GFN client, and the experience is absolutely fantastic. And later today, I'm going to actually be sharing one of the new features that we have with GFN as it applies to enabling AI for game developers. So while that's our hardware platform, that's pretty much hardware platforms. That's all I'm going to talk about today about hardware. And from now on, it's going to be talking about game features, technology, and our strategy for bringing that to game development. So the original mission for the team, and again, I started in 1999, was essentially to make stuff go fast. We would take whatever the developer had, and we would try to make it go as fast as possible. And then we started saying, well, what can we take from the film rendering world and make that run in real time in a game? So one example of that is path tracing. Path tracing is considered sort of the holy grail with regards to rendering. It attempts to faithfully simulate how light is bouncing around in a scene. Now, some objects are opaque. Some of the light will be absorbed. Some of the light will be reflected. It could be scattered in any direction. Some materials are translucent, partially or completely transparent like glass, or it may vary depending upon what the incident angle is for a ray of light to hit that, if it's transmitted or if it's reflected, with they call Snell's law is the physical law for that, how much is reflected and in which direction. So, or it could actually be, something that is translucent, where like skin, some of the light is going to go and bounce around inside the medium and then bounce out someplace, and you got to figure out where that is and how it's going to be illuminated. So it's a holistic method by which we're trying to simulate how light is transported within a scene. And the nice thing about it is that it just works. You can place any number of lights throughout a scene. You can have an animated billboard, which is illuminated and it's casting the appropriate shadows on everything in the scene. You can place millions of lights in it and everything's going to work. So this capability really takes the shackles off of artists and allows them to translate what they see in their mind's eye and to put it into pixels on the screen for their gaming audience. It's an incredible technology. So we have sped this up by 10,000 times in the past 7 years, going from Pascal to Blackwell. You can see the sort of the incremental features that we've introduced with each one of those architecture families, from the first RT core in Turing, DLSS, super resolution with Ampere, DLFG or which is DLSS frame generation in Ada, and then DLSS multi-frame generation in the latest Blackwell announcement, along with all of the accoutrement, if you will, of RT technology to make things fast. So if you're like calling, that doesn't seem quite right, we've kind of broken it down into where those speedups are, and all of these are multiplicative. So we look at speeds and feeds. This is chip size and frequency. How many SMs that you have on the chip, because you're allowed to make it larger because the process node just got that much better, and then being able to crank up the clocks as well. So we say attribute 4x to that. And again, this is going Pascal to Blackwell, sort of like a 1080 Ti to the latest that we have, 5090 in the Blackwell family. Then we have hardware ray tracing, which is afforded by the RT core and all the advances that we've done in the past 4 generations with that. We have all the software that goes around with that as well, the scheduling and everything else. We also have new features that we've incorporated for opacity maps for things like alpha-tested textures such as foliage or particle systems, where we're able to go and that much faster render things with very, very large point fields and things like that. Then, of course, DLSS, between super resolution, frame generation, and ray reconstruction, which is our denoising solution, we're able to see, again, multiplicative results of about 10x improvement. And then last, but certainly not least, there was a major development with regards to how you can do importance sampling. That is, rather than randomly sending rays out in every direction, how do you judiciously choose which rays are going to make the biggest difference to the end frame, the rendered frame? And that is like, for instance, the Riester algorithm. And that made over a 10x improvement in overall path tracing performance. And you aggregate that all up into 10,000x. So, I mean, if you had asked me 7 years ago if we would be able to do path tracing, 4K, full path tracing, including all of the rays, no rasterization whatsoever, in scenes comprised of 3 billion triangles, and I'll give you a demo of that soon, I would say there's no way, but we made it happen. And it's because we're resting on the shoulders of giants in both our research team, dev tech team, software teams, and so on. So our new missions, and this is not replacing our old mission of making stuff go fast, but this is in addition to that, there's two things. Bringing about a new era in gaming, which I've called fully immersive gaming. This is a combination of three major pillars: path tracing, I was just talking about before, neural shading, neural rendering, that's DLSS, but then also building upon that so that game developers themselves can take advantage of tensor cores within the existing 3D graphics pipeline, and then also the digital human rendering technology. But not only that, not only do we want to make games go fast, but we also want to make game development go faster. And so how do we do that? We're going to be premiering this year 3 new models for AI-driven game development, one of which is taking textual descriptions of an animation sequence and then making the animation sequence without having to do it by hand. There is localization into any given number of languages automatically with perfect lip sync. And then also models which will help for bug detection and then bug collation and deduplication. So drilling down on fully immersive gaming. So this rests on 3 different pillars, of which nobody is investing as much as NVIDIA. So path tracing, as you could imagine, we already talked about that. Neural rendering is essentially taking AI and either, I would say, accelerating or improving, if not doing both, of each various stage of the traditional 3D graphics rendering pipeline. And then digital human technology is just what it sounds like, is that creating a suite of technologies which allow the characters on screen to look, sound, and act like a real human. So prior to the CES launch, this is what our portfolio of technologies looked like, mapped into this Venn diagram. So you can see DLSS there. We have a speech recognition as well as a text-to-speech model that was available through Riva. We had our audio-to-face 3D solution. We had, RTX DI and RTX GI for path tracing, and then things like OMMs, NRD, which is our heuristic denoisers, and then shader execution reordering, or SER. Well, with Blackwell launch, we have added a ton more things, and this is all in italics, so you can see. So we have now neural shading, which is neural texture compression, neural materials, neural faces, where we're actually able to take a 3D rendered face out of a regular game engine and then make it look photoreal by applying an AI filter to it. So if you would, new models for visual language, so a VLM or a visual understanding model, as well as a distillation model for taking large LLMs that could only run on the cloud and then distilling them down for on-device execution. And then we have, of course, multi-frame generation, which debuted in the Blackwell launch. So again, this suite of tools is like something that nobody else is investing in like we are. And here's an example. This demo was developed by our Lightspeed Studios team. I named it Zora because Zora means dawn in many languages, and this is the dawn of fully immersive gaming. And let it run. Sound? You guys tested the sound. Thank you. So that was rendered in Unreal Engine 5. It's our own branch, NVIDIA RTX, which is made available. It's now shipping, available to developers. Now, this technology, which takes UE5 nanite. So nanite is a technology for taking clusters of meshes, if you will, and then swapping in on the fly various resolutions as necessary by, how large those triangles will appear on screen. And it was inherently a raster technique. Well, we've taken that into ray tracing, and we have an API, which is called Mega Geometry, in which we're able to very quickly swap in the appropriate meshes of the appropriate level of detail completely on the fly, and then generate this acceleration structure, or BVH, so that we can efficiently path trace the entire scene. There's no rasterization in this demo at all. It is completely path traced. And you can see how beautiful it is. So super proud of the team and what they've been able to do there. So neural rendering is the next step. Now, 20 years ago, we premiered programmable shading in GeForce 3. Now, this afforded the developer the ability to create their own code, if you will, that would run on the GPU for the first time. Before that, it was what we call the fixed function API. You would define where the light was in space, what color it was, what type it was it a point light source, was it spot, or whatever else. And you were usually limited to a small number of lights. It could only be 8, for instance. And so it was very limited in what the developer could do, and especially what the artist could do. So we started taking off those, constraints over time. First with vertex shaders, and then we moved to geometry pixel shaders, geometry shaders, compute shaders, low-level interfaces for managing all of these things in DX12, and then ray tracing with DirectX ray tracing with the Turing launch. Now, neural rendering is sort of a combination of what we're doing with DLSS and the next phase, if you will, which we're calling neural shading. Neural rendering is both of those together. Now, DLSS is implemented in a way where we're using CUDA code and then inserting that essentially within a black box that the developer has no access to. Now, it's received unprecedented uptake by developers because it's very easy to integrate, and it delivers the goods in terms of both performance as well as image quality. However, we would like to lift the lid, if you will, on that black box and allow developers to develop their own neural shading algorithms, which they could then use anywhere in the traditional 3D graphics rendering pipeline. And this is the way we intend to do it, is that we have a differentiable shading language that we've developed with our research team called Slang. If you intend to train anything, you need to be differentiable, because you need to be able to do backwards propagation to eliminate error as you train your neural net. And so Slang is a differentiable programming language that allows you to do that. Now, what we've also done is that we've worked with Microsoft in creating a new API within DirectX, which gives explicit access to the tensor cores from within a compute shader, and that's called Cooperative vectors. And so for the first time, not having to necessarily go through CUDA, game developers will have access to tensor cores for acceleration of whatever tiny neural nets that they want to be running on a per pixel basis. So it's very exciting technology. So without further ado, I'm very happy to introduce Sean Hargreaves from Microsoft. He's part of the Direct3D rendering team, API team, and he's going to take it away.
Okay. Good afternoon. I'm Sean Hargreaves. I manage the Direct3D team at Microsoft. Thank you for having me here today. I'm just going to talk very briefly about this. I'm really excited to introduce cooperative vectors as a new feature in Direct3D. We've been working closely with NVIDIA and other industry partners to standardize a general purpose way that game developers can access Tensor Core hardware. And this really does open up like a huge new world of programming techniques. It's kind of a cliche when introducing new things to say, like, this feature is huge, it's really going to change things. But this one really does change things, it really is huge. it feels to me like it's in the same kind of scale as programmable shaders or ray tracing. That is really just a different way of thinking about how you express algorithms and how techniques can map to the hardware. And you're going to see a bunch more material later today about some kind of early thinking about ways this can be used for things like neural compression and neural materials. I feel like that's just the starting gun of just a whole bunch of creativity and experimentation. And now that game developers have this fundamental building block, I just can't wait to see what people are going to come up with and use it for. I think it's really going to be transformative. This is coming to DirectX. We are adding support to cooperative vectors in HLSL shader model 6.9. Some new APIs in D3D12. Details can come later. That's not what this talk is about. But the important thing to know is we are working towards getting a developer preview of cooperative vectors out by the end of April, and then a final release by the end of the year. And stay tuned, follow our blog for details. That's where you'll find details as soon as this stuff is available. But yeah, it's here now. We'll be here in your hands very, very soon. Demos are running today. Yeah, this stuff's real, and I'm really excited about it.
Great.
Thank you.
Thank you, Sean. Yeah, I can't wait to see what developers do with this. I think, the sky's the limit. I mean, we're looking at replacing 100,000 lines of shader code with a tiny neural net and a series of neural textures. Doing neural texture compression, which gives up to 8x improvement over block compressed formats. But I think developers will find ways of, creating assets using generative AI, and it's encapsulated in some latent space neural form that includes no vertices, no triangles, no meshes. It's just a neural representation, which is then interpreted by a neural net running in the graphics rendering pipeline and doing some really cool stuff. So I can't wait to see what developers do with this. Sticking with neural rendering, DLSS 4 is the latest version of that. It introduced multi-frame generation, offering a 2x improvement over what we had with frame generation in Ada. And it has seen unprecedented uptake with developers. We have ramped to 100 titles in the very short period of time since our Blackwell launch, just a month and a half, which is a record for us in terms of, uptake for any feature that we've made available. In fact, it's 16 times faster adoption than DLSS 3, which I think was the previous record holder. So we're extremely jazzed about how many games, and these aren't 2-bit games, these are AAA titles. We have Indiana Jones, Enlisted, Spider-Man 2, Monster Hunter Wilds. I mean, these are big titles that are taking advantage of this. Now, you guys are probably already familiar with the benefits of DLSS, but here's just an example of how you can have your cake and eat it too. We're starting with 32 frames per second. This is Cyberpunk with on a RTX 57 Ti in RT Ultra mode running at 4K. And with DLSS turned off, it's 32 frames per second. And with it turned on, and this is, multi-frame generation, with RR, you're running at almost 230 frames per second. And, it's 1/3 the latency, which is huge, right? And if you can look at the images here, substantially better image quality to boot. So, it's both better quality, image quality, as well as substantially better performance. So really like black magic sort of stuff here. Now, RTX Remix, as I mentioned, is a product that was developed by our Lightspeed Studios team. So they don't just dog food technology, they create a modding platform as well. Now, this takes fixed function classic games and it breathes new life into them by shimming the API and then having a completely new, modern, state-of-the-art path tracing, neural rendering backend, so that you can have games that, for instance, were originally shipped over 20 years ago, and then you can have it where they automatically have path tracing and neural rendering included in them. Well, that wasn't enough. We wanted to give modders the ability to take assets, any asset within the game, remaster it, up-res it, put in new textures. It goes from 5,000 polygons to 500,000 polygons with crazy textures and, PBR materials and what have you. and replace those on the fly and then essentially remaster an entire game using the Omniverse platform to do so. And we've also included the very latest technology that we've debuted at Blackwell launch, RTX Skin and Volumetrics, and the results are amazing. So I'm going to show you a demo here. This is a community effort that is for Half-Life 2 Remake that is using Remix. Oh, he's going to feel that in the morning. Yeah, I mean, if you had asked me 5 years ago if this would be possible, that you would take a 25-year-old game and then essentially have it use the very latest technology made available to developers and breathe new life into it, I wouldn't think it was possible. So you saw some examples there, Neural Radiance Cache, where again, it's another example of you can have your cake and eat it too. Not only does it look substantially better, but it actually renders faster. And then of course, all the DLSS stuff as well. So the RTX community, the RTX Remix community have gone absolutely bonkers with the technology. You know, they're 30,000 strong. They're working over, 350 projects, 150 games. They've already published 100 mods. They've taken games that we never dreamt possible would be compatible with Remix, that were not fixed function games, and made them compatible. And there's an example that I'll be giving in a second for Left 4 Dead 2. Huge game. People are super jazzed about it. We're including RTX Volumetrics and Painkiller. And then to show how passionate this community is, they're actually training tools to up-res and improve the assets for these Remix mods and then incorporating them into Remix. And an example here is with the PBR Fusion 3. So here's an example of Left 4 Dead 2. Just briefly, and this is all very much work in progress.
Yeah.
All right, so I've covered the rendering stuff, so path tracing and neural rendering. Those are absolutely necessary, but they're not sufficient for creating that fully immersive gaming experience, because AI is going to completely change gaming experiences. It'll be, potentially acting as a dungeon master and creating the entire environment for you, knowing that what you like to play. It could be imbuing character into an NPC. It could be a coach helping you along the way. It could be an enemy, making it harder for you to kill them. You can't just go with the standard way that you would normally go about it. making games more immersive and ultimately just more fun. The problem is that replicating like humans and their decision-making process is hard. I mean, first you have to be able to perceive the world. That is the game. So you need to be able to see what's visible, what the game state is. You need to be understanding like, what's going on because, for instance, first-person shooters, you're very much attuned to what you're hearing, stereoscopically, I mean, for both ears. And then be able to go and take all of that and distill it into something that's, something you can reason on. So then once you understand what's going on within the game, you need to be able to figure out, okay, what's going on and what do I want to do? And then once I decide what I want to do, I actually need to action upon it. And then you need to have some memory there so that you don't repeat mistakes, that there's coherence. If you go to an NPC, you have a conversation with them, you don't go back in 5 minutes and they've completely forgotten who you are and so on. Well, it takes a huge AI stack to bring that to fruition. And so you can see all of these different models that we need to create to be able to make that happen for understanding video, understanding audio, generating audio, taking that audio and then being able to animate a face so that it's convincing. I mean, ultimately, you want to make it so that's indistinguishable from what you would see in a film, which is very close to reality. And you want it to span all of these different embodiments of AI in a game. AI essentially creating entire communities like The Sims. For being a companion, this is Craft and PUBG where they had like sort of what they call a CPC, not an NPC, but a CPC, co-player character that is helping you in a fight. You may want to have autonomous enemies that are very hard. I mean, maybe you could just drop an enemy into a game, which is a sandbox game, and completely change the gameplay. Then, of course, conversational NPCs, as well as how do I have an assistant that's going to help me, keep me in the game, ideally, and maybe even like bring up threats of toxicity or so on. So these are three models that we have coming to on-device, that will be able to run it actually on your local GPU. This is a visual model, which in this example, describe the image, player status, and any relevant information on the minimap, and it returns, after it looks at the screenshot, it says, player is in combat, time is 12:38 a.m., and there's an enemy directly ahead of the player. So once it has that information, it can pass it along to the next stage to understand, what it needs to do in that particular situation. And this is available now, and you can run this locally on your GPU. Here's another one, which is TTS, or text-to-speech. This is essential for anything where you don't want to have just text. You want to be able to converse, both the ASR, which is speech recognition, as well as the TTS, which is the generative part for the speech. And you want it to sound normal with prosody, that is, the way that a human would normally talk. So here's an example.
I never wanted this to happen. If only I had listened, maybe things would be different.
Right. And then the next one here is our audio to face.
Action. I've seen that before. Yes, that's perfect. They're going like 30 miles an hour. Why are you in the fast lane? Oh, that felt good, didn't it? Cut. Perfect.
So those are coming soon, next month. So we also offer some options. You can run this locally if you want. A lot of developers want that for maybe reducing latency or reducing cost, operational cost, because obviously cloud time does not come for free. And so a lot of our development partners want to run locally on device, but you can also run in the cloud. And depending upon what the capabilities are of the end user's platform, you can decide on the fly whether you want to do the computation, the inference locally or in the cloud. And I'm pleased to announce a new capability, which is kind of a third way of doing this, is that if you want to do it in the cloud, you can actually co-opt a GFN subscriber's seat in GFN, in GeForce Now, and use that for inference. So normally what would happen is that you would have GeForce Now, which would be running the entire game instance and then streaming pixels to you. In this, it's sort of like having a companion GPU in the cloud, sort of SLI in the sky, if you will, and that you're able to go and have all the inference being done there, and the developer is not necessarily paying for that cloud utilization. It's actually the end user is doing that. So we're very excited to see what developers are going to be doing with this. You can also train your own model. You can distill a model with NVIDIA NeMo. You could take, for instance, a 15 billion parameter model and then distill it down to 4 billion, depending upon what your needs are, what the scope of knowledge is necessary for your model. And if you constrain the scope sufficiently, you can get up to a 16x reduction in terms of the size. And here's an example, and we have a talk on this at GTC. That's a link there. So please check that out if you're interested. But here's an actual example of how we've worked with a game developer to bring this to fruition. We worked with Krafton. This is the same guys that do PUBG. They have a game that's coming out at the end of this month called Inzoi. It's very Sims-like. There's a community of NPCs. You give them suggestions, they action upon that, and so on. So they have taken a model and they have distilled it down to just 500 million parameters, and that's sufficient for this game, and they're running it completely on device on RTX GPUs. So super excited to see this come to actually fruition. We're also collaborating with other game studios on this technology for neural shading and so on. In this case, our good friends at Bethesda Game Studios, we've been working with them for a long time, over 2 decades. In fact, they were the first game to include GPU accelerated physics in Morrowind in 2002. I worked with them on that title. And this is just another example of our close collaboration with the game industry on trying to bring these various neural features to fruition. Roll it.
You might find it absurd, but honestly, Delage, I have never been surrounded by such a remarkable group of people, present company included. It has been a very long time since I have been someplace that could possibly feel like home. There are worlds beyond count out there, but that feeling is rare and precious.
So humans are very attuned to faces, and which is why I wanted to focus on faces first for this type of technology. I mean, from birth, we're attuned to whether a face looks right or not, and that's what they call the uncanny valley of something looking more or less right, but absolutely not looking like a human. And so we've solved that for offline rendering for film. I mean, films these days are convincingly, I'd say, photorealistic with few exceptions. But for the real-time realm, you only have a very small amount of time on the GPU to render the face, and crossing that gap has proven to be extremely challenging. So this is where neural technology comes in. We have pairs, sort of a lo-fi and a hi-fi version of both faces, and for various poses, camera angles, if you will, various occlusion, maybe it's like a hand or another obstacle in front of the face, various lighting conditions, self-shadowed, light coming from one direction or another. We have a curated and a very augmented data set that we create a neural model that we then replace the face with, using the original face as, of course, the reference. And so this is the first generation of the technology. It's not quite there, but it's very promising, I think, as a first step in sort of closing that gap of the uncanny valley between what you can do in a game and what you can do in film. And we have a talk on that tomorrow. Nathan Hubler will be doing that, and I'll give you a reference in a sec. So we're very excited to be working with Bethesda on this technology. Now, I was saying assistants, I think, are going to become ubiquitous in gaming within the next few years. You want to be able to onboard, bring people onto a game as quickly as possible. You want to reduce churn, people dropping off. You may want to monitor toxicity that they're subjected to. You may just want to help them figure out how to beat a boss that they've been struggling with for 3 hours so they don't just burn out and rage quit the game. So I think that these are going to become ubiquitous. And then the question is, how do we bring the technology? So we have blueprints for this, so we can work with the game developers on incorporating this technology directly in their own game. And we also have a G-Assist platform that was announced at Computex last year, which is a way to do that as well. So to sum up things with regards to fully immersive gaming, we are paving the way with all of these technology offerings. We have the neural rendering, which is composed of the neural shaders that Sean was sharing with you, exposing tensor cores within the compute shaders so that in combination with a differentiable shading language, that developers can do a DIY neural solution for anything that they want in the 3D graphics rendering pipeline. And then, of course, DLSS, 4 generations now and going strong. Path tracing is sort of table stakes. I think every title in the next, probably 5 years from now, anybody who cares about image quality, it will be path traced. Go out there and just say it. It is just so much easier for game artists to be able to create what they see again in their imagination and taking that into a game when they have path tracing available to them. Digital human technology spanning audio to face, speech recognition, text to speech, small language models, all of which can run on device. The neural faces stuff I showed you, as well as all of the skin and other technology that we have for hair and such. And then obviously the Remix platform, which allows people to breathe new life into old games with the latest in technology. So I say, wait, there's more. So yes, fully immersive gaming is one of our new strategies, but also how do we help game developers with the game development process? How do we accelerate game development itself? Well, games are becoming more and more complex over time. Essentially, every decade, there's an order of magnitude, larger scale, more geometry, larger maps, more characters. And it's becoming prohibitively expensive for many game developers to keep up with that pace. Just as a reference, the Zora demo that I showed you, it consists of 3 billion polygons. And this is in a fairly small space. If you would then go and expand that to something like the size of an Assassin's Creed map or Starfield, you would be talking about trillions of triangles. But on screen, we're looking at 500 million triangles. So the question is, how can we create models, AI models, to help game developers with the game development process? Well, you got to start somewhere. We're not going to boil the ocean. So 3 areas that we thought would be valuable to game developers and a wide spectrum of game developers was animation, localization, and QA. So I'm going to go and dive into each of those. So we have a model called AI body motion. Now, this takes text, and it can also take poses which are given by the artist, and then it creates an animation sequence that you can then incorporate into your game. So I'm going to go and roll a video here that's going to show you all about it. This is John Malaska, who is our product manager for AI body motion.
AI body motion is a new generative animation technology from NVIDIA that helps accelerate the animation workflow while retaining full control. Let's create an animation for our scene here in Unreal Engine. We'll build the animation in Autodesk Maya using our developer reference plugin and connect it to Unreal via LiveLink. To start, we want to get the character to jump over this low obstacle. First, we need to create a text prompt to tell the character what we'd like them to do, and we'll generate 4 variations and choose the best one. And there's one in here that looks good, so let's select that and bake it to Maya's human IK rig for further editing. So now we have the character jumping, but we want to control the posing and timing in more detail. And we can achieve this using pose targets. Pose targets tell AI body motion what parts of the character pose it should maintain when generating animation. The full body pose target maintains the entire character's pose. There are also sparse pose targets that keep key body parts like wrists, ankles, and the root in place. When set, body motion generates a new pose for the rest of the body while maintaining these positions. For our animation, we'll use the root pose target to adjust the landing position and direction, and a full body pose target to customize the key pose within the jump. Now let's get the character walking over to the other side. To do that, we'll enter in our new prompt, and then we'll set a full body pose target segment on our jump animation to prevent any changes when regenerating. Next, we'll reposition and set a root pose target on the other side. However, when we generate, the character is walking through our world geometry, so let's fix that. We'll add in a new root pose target to avoid the object. With the pose target set, we can generate the animation again. And there we go. The character now properly walks along the path and not through our world geometry. But maybe we got a note that now the character needs to sneak along the path. No problem. We don't have to go back to the drawing board. We'll set a root pose target segment during the walking and adjust our prompt. This enables us to generate with a new style while maintaining the same path. We can also use AI body motion to create quick and seamless transitions into existing motion capture animation. First, we'll create a full body pose target segment to prevent changes to our existing animation. And then we'll preview our clip in the Maya time editor. And we'll set another full body pose target segment that matches the motion capture clip length to prevent changes when generating. And then we'll create a quick prompt around the transition space and we'll generate. And there we go. In just a few seconds, we've created a believable transition to our motion capture clip. And we can take a look at the final animation, start to finish, and see what it looks like with our Unreal Live Link. And AI body motion is a technology that can be integrated into any product, including game engines like Unreal Engine 5, which we built another developer reference plugin for. Here, we're leveraging the Unreal Engine sequencer to create our prompts and pose targets. The generated animations can be modified with Unreal's control rig system for retargeting and further editing. We encourage you to explore our developer reference plugins to customize body motion to fit your specific needs. With AI body motion, you can create digital human animations in a fraction of the time, significantly streamlining your production process. For updates, please sign up at developer.nvidia.com/ace.
Yeah, so like John was saying, you can apply or sign up for updates on our website, and this model will be available to you later in the year. It will be licensed under the standard NVIDIA AI Enterprise license. All right, so audio to face, I talked about this already. You can also plug this similarly, just like with AI body motion, plug this into any engine that you have, whether it be bespoke or we'll have reference into Unreal Engine. Here is an example of the latest diffusion model, which offers a lot of image quality improvement on the lip sync.
All right, team, we can do this. Let's give it our all no matter what. We've got this. I don't know what to do anymore. It hurts so much, and I just need someone to understand. We've lost so much, but we will not be defeated. We stand together, and we fight for our future.
Yeah, you can particularly see any time where she purses her lips together, like ma, ba, pa, that it's much more accurate in the new diffusion model. And here's another example where we're using it for turnkey localization.
In this game, every move is calculated. Our decisions now will define our future. 在这个游戏中，每一步都经过精心计算，我们的决定将决定未来。Dans ce jeu, chaque mouvement est calculé. Nos décisions maintenant définiront notre avenir. Iskelme, 哈格登索什么即可乌太亚站，哈马为年年，阿帕马为百夫之个巴伊瓦西可恩见。
My Chinese and my Indians, or Hindi is not that great, but the French sounded good to me. So games are getting larger, as we talked about earlier. They're getting more and more complex, and so just obviously the QA burden is extremely high for these. Just making sure that, things in the environment look right. There are things that aren't interpenetrating. There are things that aren't floating or in another way looking uncanny. And, you can't just, multiply your QA team by the same factor of how much larger the world is that you're creating. So you need to be able to use tools to automate a lot of this. So we're looking at what sort of things could we do that would help game developers out. And one of which is it's essentially a visual model that will spot bugs and then be able to go and provide a textual description of that bug, and then a summarization capability which will collate, deduplicate those bugs, and then summarize them for the QA engineer to review, and then ultimately determine if it was a false positive or it was a legitimate bug or what have you. So we have an example of this here, running an alpha version of Cyberpunk. We're working with CD Projekt Red on this, and you can kind of see, I'll let it run. So this is with QA detection off. You can see some kind of wacky stuff going on. And so this is kind of what it's with QA detection on. Let me try to pause this. So, oh, nope, that didn't work. Okay. Yeah, so, yeah, duplicate. Let's see, try to go here. Fail. Okay, here we go. So what it's doing is it's spotting here that, these characters look identical. So it's saying that there was a duplicate NPC here. And it does all of this automatically. Okay, and then it sees that these guys are wedged. And then it sees that this guy is standing on a dumpster, which I would argue in San Francisco is probably completely normal. But for most games, you would not expect the NPC to be on a dumpster. So these models are currently in development, and we're going to be making them available by the end of the year. All right, to sum up, these are all of the talks that we have. They're all in the same room, which I believe is upstairs, WH3009. It's going to cover a lot of the stuff I discussed already, but it's going to go deep into the details of how we built Zora, how to go and apply neural shading to various applications. We have some postmortems that we did with gaming integrations with path tracing. And then, mega geometry stuff as well. And this was the first one, crossing the uncanny valley with neural face rendering. That was the one that I showed you, the research collaboration with Bethesda. We'll go deep dive into the Inzoi, next-gen agents, SLMs, and then, again, some other postmortems and so on. And not only are things going on here at GDC, but due to conference management, I thought I had the GTC stuff in here as well. Maybe it's the next slide. So we have GTC content as well that you guys can go and look at on the web. You probably saw that there is a business card. You can scan that, or you can scan this. We have a 5090 that's been signed by my boss that you are eligible to win, but you got to enter. So go to that site, and please do it by 2 p.m. if you want to win. You got to fill out a short survey and put in your contact information, and best of luck to all of you. And then, here it is, featured gaming GTC talks, a number of things that I mentioned already. I'll call out the watch your language, create small language models that run on device, which is the one I had cited earlier. So to wrap things up, AI is transforming the way games are developed, and it's going to transform the way that games are played. And we're here to help you. It's bringing to bear truly immersive gaming experiences, fully immersive gaming experiences, combining path tracing for realistic light transport, neural rendering to take those signals and then make the image look absolutely amazing, as well as sort of lifting the black box so that game developers themselves can innovate and take advantage of all of the capabilities of the GPUs like tensor cores and so on. I agree with Sean. This is going to be a step function in terms of creativity well beyond what we saw in programmable shading. And then all of the technology for digital humans to have them so that whatever role they play in the gaming experience, that they look, they sound, and they act like real human beings. And then last but not least, putting together a suite of AI models and tools that will accelerate game development itself. So thank you for your attention today, your presence, and I wish you a great GDC.